Hello, everyone. Welcome to the Toronto Geometry Colloquium, a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we're going to have one opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And today's topic is really forward-looking. Our opener, Emilie Yu, is going to talk about CASI, a curve and surface sketching in immersive environments. And our headliner, Dr. Duygu Ceylan, is going to talk about neural dynamic characters. And if you have any questions, please leave comments in the YouTube or in our Discord channel. So first, let me introduce our opener, Emilie Yu. And she's a PhD student in the Graph Deco team at INRIA, supervised by Dr. Adrian Bossu. And personally, I'm a huge fan of her work and the 3D art she created. And her research is in 3D modeling. But instead of focusing on the traditional interface, like using mouse to click and drag shapes on the computer screen, and she focused on 3D modeling in the immersive environments, such as virtual reality. And this problem itself is super hard because in order to do 3D modeling in the virtual reality, it requires humans to kind of draw things in the mid-air, which is much harder than drawing shapes on a piece of paper. But fortunately, today, Emilie will present a great solution to this problem. So please join me to welcome Emilie to talk about her work, CASI.
Hello. Well, thank you, Derek, for this really kind introduction. Just share. All right. So yeah, today I will present our work on CASI, curve and surface sketching in immersive environments. This is joint work with these few great people from INRIA in France, Technical University of Denmark, and DGP Lab at Toronto University. First, let me give you some context about this work. So designers often go through two different steps when developing a concept. First, they explore ideas by loosely sketching on paper or with a pen tablet, or even in this case that I show, VR sketching. And then for some of their initial designs, they will refine and detail the shape using 3D modeling tools, such as polygon modeling here, to produce surfaces suitable for rendering and rapid prototyping, for example. In this two-step workflow, the first ideation sketches are often not reusable at the 3D modeling step, other than as some visual inspiration or for manual tracing. For example, here the gray patches are created independently from the pink strokes, which are used only as a visual reference. Even though the pink strokes already precisely describe the shape, the designer has to redefine the geometry all over again, pretty much. In this context, we want to explore the possible synergies and bridges between 3D sketching and 3D modeling. And in the project I present today, we prototyped a VR interface to create strokes and surfaces using 3D sketching as a prime interaction modality. While previous work has dealt with the problem of surfacing 3D sketches, they mainly focused on sketches defined as well-connected curve networks. But the thing is that when sketching in 3D space, as Derek mentioned, it's actually pretty difficult to create precise intersections between strokes because of some imprecision due to mid-air sketching, as you can see highlighted in this hat sketch. And this makes it impossible to directly apply those methods to a sketch. Some methods have explored beautification of 3D sketches before. So if we could kind of beautify or structure automatically a sketch, then it kind of becomes a curve network. But the thing is with this method that they either relied on manual user interaction to detect potential intersections, or they were limited in the type of curves they support. So either they focus on planar curves or lines and circular arcs. On the other hand, we strive to support even non-planar freeform curves as can be found in this sketch. So in our sketching system, the user strokes are automatically neatened as the sketch to form a clean, well-connected curve network. By analyzing this evolving curve network, we can create surface patches, lofting the sketch wherever we assume that the user wants a patch to appear. This makes it possible for an artist to create a wide variety of 3D concept models by relying almost exclusively on sketching strokes as input. This system is composed of two separate components. First, we propose an automatic neatening scheme capable of structuring each input stroke on the fly to connect it to other strokes in the sketch, while minimally deforming the initial shape of the stroke. Secondly, we continuously analyze the curve network to add surface patches to the sketch. I will provide some details on each of these two steps now. Neatening the input strokes is cast as an optimization problem where we set two objectives: deform the strokes as little as possible to preserve user intent, while enforcing as many intersections as possible to get a well-connected curve network. We first detect an overly complete set of potential intersection constraints by looking at previous strokes that are close to the newly sketched stroke. So in this drawing, I drew these intersection candidates as the black dots. And then we can select the appropriate subset of constraints to reach a balance of both fidelity and connectivity objectives. We do that efficiently via a greedy search based on evaluating smaller and smaller subsets until the energy reaches a local minimum. Once we have selected the intersection constraint points here in black, we look for the new stroke S prime that passes through those points. But still, we wish S prime to stay close to the shape of the input stroke S. We represent these strokes as one or multiple cubic Bezier segments. So we find S prime by solving for the control points that generates a curve that best resembles the input stroke while respecting these hard positional constraints given by the intersection points. Creating the appropriate surface patches is then done by maintaining a parallel graph data structure for the sketch, which is updated whenever a stroke is created or deleted. In this graph, the patches that we're looking for correspond to cycles, or closed loops of nodes. While efficient methods to find such cycles exist, as I mentioned in previous work, these methods typically work on a complete curve network on which they perform a global search. In contrast, our curve network is incrementally created, and we wish to have the patches appear or disappear as the user sketches and not only at the end. So what we do is that we launch local searches for relevant cycles whenever we update the graph. When we detect a cycle, we triangulate its boundary curve to get the surface using an existing method proposed by Zhou and colleagues. We can then display the patch as a semi-transparent surface, increasing readability of the sketch by providing some occlusion cues. For the local cycle searches, we have to take care to only select cycles that correspond to surface patches envisioned by the user. As you can see in this simple sketch of a 3D capsule, some cycles shouldn't be lofted as they don't correspond to the outer boundary of the shape. To efficiently select the correct cycles to loft, we will proceed by greedily choosing a path across the graph that forms a plausible cycle. For example, let's say the blue curve was just added to the sketch. We start our search for a cycle on this graph edge. Then, at the intersection, we can sort the curves based on the angular coordinate in the tangent plane of the surface at this intersection point. This indicates which stroke should be the next in the cycle, which is this one. And walking along curve segments in this manner, we can finally recover a cycle. Since this simple method relies on correctly estimating the tangent plane of the underlying surface that the curves lie on, it can fail near sharp feature curves, for example, where the tangent plane at the intersection point is ill-defined. So we complement this rather simple method with the possibility for the user to manually add or delete a patch by clicking at the approximate position of a missing or extra patch. To evaluate the novel features of our system, we finally conducted a remote user study with 12 participants, half of which were amateur or professional artists familiar with VR sketching or sculpting, and the rest were novices, but everyone was familiar with using VR interfaces. We made them use 3 variants of our system. In freehand mode, users could sketch without any additional features. In amateur mode, users would see their strokes neatened. And in patch mode, users would see stroke structuring and patch creation. We find that our novel features are able to support users' creativity on par with unconstrained freehand sketching. And further, we noticed that the automatic creation of surface patches encourages the users to create well-connected curve networks. But on the other hand, automatic curve Newtoning reaches its limits on some very detailed sketches, and some users experience excessive Newtoning on smaller scale details. Secondly, the incentive to create well-connected curve networks in the patch system was experienced as a constraint by some, since they were forced to think of their designs in terms of a curve network. And the thing that we saw is that when participants were sketching the fully constrained system, they were sometimes constructing their sketch in ways that did not always resemble a curve network, such as by using on-surface decals or having very over-sketched zones, as you can see on these shoes. So in future work, it would be interesting to explore semi-automatic sketch Newtoning user interfaces that give the users more control over the results. For example, in a recent UIST paper, Scaffold Sketch, users can define precise and deliberate geometric constraints through the use of construction lines. Secondly, we believe that there may be an interest in developing sketch interpretation and surfacing techniques that do not rely on the curve network paradigm, relieving artists from having to build their sketch in this very particular fashion. But still, we feel like CASI is a good step towards building more bridges between the loose and freeform art of 3D sketching and a more constrained step of creating an actual 3D model. If you are interested in this topic, I'd highly recommend to tune in at the Colloquium in 2 weeks for a full session around VR tools for creation, where Suyu will present her paper that I just mentioned, and my collaborator Rahul will dive deeper into the unique challenges and opportunities surrounding this medium. Thank you for your attention, and I look forward to hearing your questions later.
Thank you, Emilie, for the fantastic talk. Especially the GIF are super great for explaining the process, explaining the difficulty. Thank you for the talk. And so now we will proceed to the talk of our headliner and have a joint Q&A at the end. So it is my great honor to introduce Dr. Duygu Ceylan, and she received her PhD at EPFL with Professor Mark Pauly, and now she is a senior research scientist at Adobe Research. And her research focused on applying machine learning to all kinds of geometric problems related to human characters. For example, how can we turn a rough 2D sketch as the input and synthesize realistic human hairs? Or how can we use neural network to add details to a core simulation of a garment? So personally, I'm also a big fan of her work on adding secondary motions to human characters. And the importance of her work also make her the recipient of the Eurographics Young Researcher Award last year, and also millions of other awards I don't have time to mention. So instead of taking too much of her time, please join me to welcome Dr. Duygu Ceylan.
Thank you so much, Derek, for that nice introduction. So let me share my screen. Okay, great. Yeah, I'm very excited to be here to talk about some of my recent work on modeling neural dynamic characters. And Derek already gave a nice introduction. Just to recap, I did my PhD at EPFL in 2014, and since then I've been a senior research scientist at Adobe. And some of my work at Adobe around 3D face fitting and tracking and human body pose estimation has shipped in various products. And basically, this is a result of the research I've been doing on mostly in 3D perception. So to give you a little bit more context, my research generally focuses on the problem of 3D understanding from images, videos, or sketches. And I'm specifically interested in 3D perception for humans. For example, you see this person who is standing, the physical spaces. Here you see a table, a couple of chairs, and finally how humans interact with each other and these physical spaces. Like this person is, for example, sitting on the chair. So why am I interested in building such 3D perception algorithms? Well, as we all know, we are living in an era where digital worlds are basically dominating both in our professional and also in daily lives. And I believe that 3D perception is basically very important for two main tasks. One is to be able to build more intuitive 3D workflows. For example, how do we make it easier to create, edit, and author 3D content? But it also enables more intelligent 2D workflows, like, for example, enabling some authoring operations that would not have been possible without 3D understanding. So let's talk about a few specific applications. For example, I mentioned about intelligent 2D workflows. So let's think about editing our images, videos, or other digital content. But we know that humans are actually one of the main subjects of such content. Actually, 1/3 of Adobe stock images, which is a big image database, contains at least a single person. And similarly, Instagram Stories has around 500 million active daily users. And you can imagine that most of the content that is shared does have human subjects. So think about now all this appetite and desire to build intuitive, human-centric editing workflows. And that's why it's no surprise that some of the most popular editing apps on our mobile devices, as well as more sophisticated tools like Photoshop, has focused on building these human-centric editing tools, and these require understanding humans from images. Editing is not the only application. We are spending most of our time in these virtual connections these days, and we all have similar desires. We want these connections basically to feel more human. And one of the technical components that will enable this is to be able to digitize, model, animate, and finally render humans as realistically as possible. And one other application could be animation. Think about all these characters from your favorite animated films and why are they so memorable? Well, as people, we like to personify. We like to personify with characters who have their own personalities, but who also act and move like humans. So understanding, the 3D understanding of humans, how they move, how they interact, is also very important for such applications. So we can make a much more crowded list of such applications, but basically, I think you get the idea. So motivated by all these applications, my research basically has focused on developing tools to understand humans and characters, like human bodies, their garments, dynamics, as well as understanding physical spaces, mostly in the form of analyzing human-made objects. And finally, the interaction between the two, like how does a person interact with a scene and so on. So today I will be mostly talking about my work in this space of modeling and understanding dynamics of humans and characters. And before I dive into details of some work, I would like to also cast two research questions that I'm particularly interested in answering with my work. So since my work focuses on 3D perception, I guess the first question to ask is what type of 3D representations should we use? And as you all know, there are many alternatives, each come with their own pros and cons. And most of the machinery that I'll talk about relies on data-driven and machine learning approaches. So a big question there is, how do we develop algorithms that can generalize beyond our training corpus? So let's keep these two questions in mind and now do a deeper dive into some technical details. So first of all, I would like to basically give a summary of what is the current state of the art. The state of the art has actually advanced quite a bit in terms of 3D human body shape and pose estimation. There are many methods that work with single images or monocular videos. And most of these methods try to predict deformable human body representation from even just a single image. And I think this is very impressive and exciting, but it may not always be sufficient to model some person-specific features or all the dynamics related to humans. So for example, here we see an example image. Even though this is a tight-fitting clothing, if you look closely, there are many of these interesting wrinkles and folds on the pants the person is wearing. So how would we, for example, model such details? If you look at her hair, what is a good representation for hair, and how would you model its dynamics? And in this particular case, she has these interesting strings coming from her top, and imagine all the secondary motion they will undergo as she is walking, for example. So all these challenging questions basically have motivated me to think beyond faces and naked bodies in the past few years, and I started looking into how do we model some of these dynamics for humans and characters. So let's look at a traditional pipeline first, like more specifically in the context of garments. So usually the process starts with modeling a garment. Once you have this, then given some underlying human body motion, you can simulate it to basically deform it with the person. And then given some desired viewpoint and some like desired lighting conditions, you can render it to get that final appearance. And as you can imagine, the simulation step is pretty critical here because this is where all the modeling of the dynamics is happening. And currently the go-to solution for this is using a physically based simulation process. And this is because it's actually gives us a very accurate modeling of the dynamics. On the downside though, like depending on our application, it may not always be the most efficient solution. And some applications may not require very accurate physics, but maybe you just want some plausible dynamics. Maybe you are interested in providing a fast preview, or anything that looks plausible might be good enough. So that's why I feel neural simulation can come into place and basically play a complementary role to physically based simulation. So this was kind of our main motivation when we did this work on using neural networks to enhance the details of garment simulations. So here you see an example garment that is simulated with a physically based simulation. Basically, you see a simulation that uses only a coarse underlying mesh, and also a simulation that uses the original high-resolution mesh. The high-resolution simulation is not only slower, but it's sometimes also not very robust. So basically that motivated us, like, what if we start with this coarse simulation, which is fast and not so prone to like errors? Can we now augment this with plausible details in a post-processing stage using neural networks? And to make the problem statement more clear, basically our input is the result of like the deformed state of a garment that we obtain by running a physical simulation using a very coarse mesh. And we represent this as the normal map of the garment. So the input is this coarse normal map. And as output, we want to obtain a more enhanced normal map that contains these rich wrinkle details. And why do we think we can actually achieve this goal using neural networks? So here are some observations. You see an example skirt that is simulated in two resolutions, a coarse and a high resolution. And you can see that the overall shape of the skirt does not change much. So it seems that it might be sufficient if we focus on the local details instead. And looking at those local details, even though they are not very apparent, the coarse simulation actually still has some cues that I for example, highlighted some regions in orange. So our hope was that, okay, the neural network can pick up those cues and try to sharpen those details and augment them with some additional plausible wrinkles. And I think the main motivation and the contribution was like, how do we cast this problem of detail enhancement? And we basically got some inspiration from all the style transfer related work that is happening in the vision community. So what is the connection there? So again, here you see an example skirt that is simulated with coarse and high resolution meshes, their corresponding normal maps. So basically our hypothesis was that these coarse and detailed normal maps will follow certain statistics in some neural feature space. So they will fall into some specific feature distributions. So our detail enhancement can now boil down to basically finding this transfer function that would map from one distribution to the other. And basically we kind of verified these hypotheses by running examples of coarse and detailed normal maps through some neural networks, looking at some of these embeddings of the feature space to see whether there was like those patterns, and it turns out there is. So basically, given this motivation, then the goal is, okay, can we now design a network that takes coarse normal maps and in fact just patches from these coarse normal maps and then gives us a much more detailed normal map. And similar to style transfer tasks, we try to define two types of losses. Like one is content loss. So in our case, this means we want to preserve the original course flows that are already there in the course simulation. And the style in our case basically boils down to learning details for a particular material from examples of simulations at training time. And the style loss tries to encourage synthesis of additional wrinkles. And we observe that there are usually two types of wrinkles that are synthesized. One tries to sharpen some of those that we already see in the course simulation, and the other tries to generate some additional wrinkles by looking at the neighborhood regions. So that brings us this overall pipeline. We basically start with the coarse geometry of a garment, and we represent it as normal maps. And then patches from these normal maps go through a detail enhancement network, and then we obtain these enhanced normal maps. As we all know, the simulation also depends, the simulation result also depends on the material type of the garment. So that's why we have this additional input, which determines the material properties that goes as input to this network. So at test time, as a user, you might already know the material type. If you don't, we also introduce this material classification network that looks at the results of your course simulation and then classifies the material of the garment. And once you have your enhanced normal maps, you could either use them just for rendering purposes, like doing normal map baking, or you can integrate them back to get your final geometry. As I mentioned, this detailed transfer networks takes this additional information of material. So how does it work with different material types? And again, we draw some inspiration from the style transfer literature. Usually in like image style transfer tasks, people introduce these adaptive layers. Basically, the idea is you train your network and then you introduce new layers that adapt the weights of the network through some basic shifting operations. So we do something similar. Based on the material type, we adapt the weights of the individual layers of the network so that the network can work with different material types. So how do we train such a network? This network really just works on the local patches of a normal map. So this is useful because then the network can adapt to different like layouts of the garments in the normal map space. And it also helps like when designing the training data, we can basically keep it rather simple. And in our case, we actually trained it with like some simulation of some single sheet of cloth and some very basic skirts. And at test time, we can now try it on more complex clothing, like in this case, some pants, shirts with hoodies, etc. And the network can generalize. So here you see the input course simulation and the results of our method where we have added more like rich details. And here's another result, which is this like multi-layer skirt, which is not so easy to simulate with a very high resolution mesh, but the network is able to do a decent job. So in this whole pipeline, we still have the physical simulator in place. It is used to obtain these initial course simulation results. So we had this follow-up question like, what if we don't have any simulator and let's say we start with some skinning-based animation, would this pipeline work? I mean, looking at this result, the network, yes, it does generate some like wrinkle details, but we are not really changing the overall shape of the skirt. So that's why if you look at this animation carefully, the skirt still feels quite stiff due to this restriction. So this kind of motivated us to look at this follow-up work where we particularly wanted to ask, okay, starting from a skinning-based animation, can we now use neural networks to add additional plausible dynamics? So more specifically, the input is like skinning-based animation of a 3D character. And then as output, we want an animation with additional secondary motion, for example, to mimic the motion of some soft tissue dynamics. Here, I hope it's coming through the streaming, but like you see some additional dynamics on the head of the character, etc. So what is a good solution here? Like we want a method that is fast and efficient. A method that is general, like that we could apply on different mesh topologies at test time, and something that is controllable. Like as a user, it would be great if we could control how much additional secondary motion is generated for the different parts of the character. So how is this done typically? So this is usually done using like some simulation methods such as like finite element methods. And these methods often work with like volumetric meshes of the character. So here you see an input volumetric mesh of a character. And let's say the positions of the vertices in the original skinning-based animation are X. And then we also define these additional properties for the vertices, like their mass and stiffness. Stiffness in particular will determine like how much additional motion will be applied. And our goal is to find the new positions of these vertices that we call U after applying some additional secondary dynamics. And this is usually the result of constraining certain parts of the mesh. So basically, you define some constraint regions, and in those regions, you want the vertices to preserve their original motions. And these constraints basically result in forces in the rest of the mesh, creating the secondary motion. And the two main forces are, one is self-inertia. Basically, the vertices tend to keep their state of motion. And then there are internal forces between neighboring vertices that try to pull the mesh back to its rest shape. And when these forces are in equilibrium, basically you reach the state with the final positions of the vertices. I think we don't need to go into more details, but basically the point is there are these two different type of forces that determine the final state of the mesh. And our method basically draws inspiration from this physical process. So basically we wanted to design a neural network that can somehow mimic these two types of forces. So basically for each vertex in our mesh, so let's look at this vertex in red, we define a neural component that would basically map this vertex, some properties related to this vertex, such as like position, velocity, acceleration, etc., to a latent space. And we hope that that latent space is a good representation of the self-inertia. And similarly, we define additional network components that is defined for every pair of neighboring vertices. And we hope this learns to map the properties of our mesh to a latent space that represents the internal forces. And then basically we have this final network component that gets the output of the first two components and then predicts the final displacement of the vertices. So basically, really the motivation is to design this network architecture that tries to mimic the physically based process. So we can try to now define such networks for the whole global mesh, but that means we will end up with networks that are big and also not very easy to test across different mesh topologies. So we make basically a locality assumption. So assuming that at a very small time interval, the state of a vertex will be mostly affected by its wandering neighbors, we design our network to work on local patches. And if you look at the patches like in these volumetric meshes locally, patches from a sphere are not too much different than patches coming from like a humanoid type of character. So basically this has two advantages. One is we have a lightweight network, and also we have something that generalizes to different mesh topologies. As a result of this assumption, we actually train this network only with spheres, with some random motions applied to the spheres. And then at test time, we can basically run it on different character meshes. In this case, these are some examples from the Adobe's Mixoma dataset. And finally, we wanted something that we could control. So as input to our network, we also give the properties of the vertices, like their mass or stiffness. So at test time, you can paint different properties to get different secondary motion. So in this case, like darker red means you have less stiff areas, which result in more secondary motion applied. Okay, great. So in these two works, basically, I mostly focused on the simulation part, and in some applications, we might be interested in the final appearance, that is the result of the rendering process. So I'll quickly go over some recent work where we try to look into this problem of simulation and rendering jointly. So more specifically, what we wanted to do was, like, for humans and garments in particular, given an underlying human motion sequence, can we try to generate how a garment would look like? How do we model the appearance of that garment? In the previous work, we use basically either coarse simulation results or skinning-based animations as input. And in this work, we tried a different approach. We said, okay, what if we have a coarse garment proxy? And this coarse proxy is not only a lower resolution version of the garment, but it also lacks like geometric details. Like this is, for example, a skirt with many multi-layers, but our coarse garment proxy could be just a plain skirt. Can we now learn neural features and combine with neural rendering to synthesize how this target garment would look like? So the overall pipeline is we start with this human body motion sequence. The first step is basically to learn how our coarse garment proxy would deform. And this we could either do based with simulation or use another network to create this. And then can we learn some neural features on top of that coarse garment so that we bridge the gap, the appearance gap between our coarse proxy and the final target garment and be able to simulate and render out the target garment appearance. And how does this work? Basically, maybe I'll skip this part very quickly. We have a very simple network architecture that first predicts the shape of our coarse proxy. But the more interesting part is like, if we have this coarse template and we know how it deforms, how do we go from there to the target garment appearance? So basically, similar to some recent work in neural rendering, the idea was, can we learn some neural features, or let's call it some neural texture? And this neural texture basically will help us to bridge the gap between the appearances of the coarse and the target garment appearances. But it's not sufficient to learn just one global neural texture, because we know that the appearance also changes with the human body motion. So basically, we also bring this component that learns motion features, and then we combine this with the neural texture to render out our final neural features on the garment. So these neural features basically move as the coarse garment deforms. And then we have a neural renderer that takes these neural features and then synthesizes the final appearance of the garment. And this neural renderer basically looks at previous frames to ensure that we have more temporally coherent results. So very quickly, these are like some examples. Here we show that starting from the same coarse garment proxy, we can train two different networks that basically adapts to the appearance of two different types of target garments. And this network is trained with only like a very short sequence of motion. So basically the idea is at test time, you perform some simulation for a short sequence, and then during training time, and then at test time, you can generalize to unseen motion sequences. And we also showed that this can work well, not just with like simulated synthetic data, but with real data as well. So here we have this example of a character which has mostly tight clothing. So in this case, we use the underlying naked body as our coarse template, and then try to synthesize the final appearance, including like all the clothing deformations and so on. Okay, great. So we have seen some works. Now maybe let's go back to some of the questions we had and see if we were able to answer them. So one question we had was like, what type of 3D representations to use? In the two works that I shown in the beginning, we were using explicit 3D representations like normal maps or meshes. And these have some advantages. I think they are easy to control. We can attach some semantic meaning to them. The downside is they may not be easy to capture details, or you need to increase the resolution. And that's why in this last work, basically, we try to bring some neural features into the equation to be able to capture more details. So in parallel, there is also quite a lot of work on hybrid representations, on implicit representations, sorry. And implicit representations tackle some of the disadvantages, like they can adapt to different topologies, they are suitable for details, and it also turns out neural networks are good in predicting them. The downside is they may not be as easy to interpret. So I think moving forward, we will see more and more maybe hybrid representations for humans and garments specifically. It feels like deformable templates are good for modeling the underlying body, and then maybe using implicit representations or neural representations to model garments seems like a good choice. Another question we had was, how do we generalize our algorithms? And I kind of like touched upon this in the two works. Basically, we were using these patch-based representations for better geometric generalization. And I think this is great, but it's still limited. For example, for this secondary motion work, the network that was trained only on spheres is not really able to, like in this case, model the dynamics of the ear of this mouse, which is more like a thin surface. So I think it's still an open question, like what type of geometric primitives would be sufficient to cover a broader range of test cases at test time. I think geometry generalization is something where we have more understanding of. I guess generalizing to unseen motions, I feel might be a bigger challenge. So like similar to, for example, PCA basis for geometry, some ideas that I have been thinking are like, is there a good set of motions to use during training so that we generalize better during testing time? Like, can we learn some good motion bases? And I know there's quite a lot of work in the animation community for motion graphs. It might be interesting to maybe look into that and get inspired. And like similar to this locality for geometry, maybe we also need to come up with some local motion basis models, like maybe the arms, the motions that are needed for arms might be different than the motions for the leg region. I think I will skip these so that we have some more time for questions. But before concluding, I just wanted to briefly give you also a quick glimpse of Adobe research. So some of you may already know Adobe has various research offices across different parts of the world, mostly in the US. I myself was previously in the San Jose office for the past 6 years. I recently moved to London. So in London, we have currently a small but growing research group looking at problems in vision, graphics, machine learning. We are getting close to the internship season. So if you are interested about opportunities, feel free to reach out to me or my colleagues. And yeah, with that, I want to thank you and also want to mention that like most of the work that I showed today is really done with many interns, academic collaborators, and other colleagues at Adobe Research. And yeah, let's have more discussion now.
Thank you both for the really great talk. And we already have a bunch of questions, but if you still have more questions, please feel free to leave them in YouTube or in our Discord channel. So yeah, so first I'll give Duygu a break and then start with a question for Emilie. So this is like perhaps a relatively detailed question, is that if we want to have an open surface instead of like closed surface, how is your method allows us to do that?
Yes, it does. So the user can delete a patch, like if a patch is like if you are drawing a sphere and then you have patches on like all your patch of sphere, and you could just delete one of the patches and then it's an open sphere. Yeah, so in that way you can do it kind of manually through user interaction. Yeah.
Well, that's simple. And the other is also related to the detail of this method, is that how does the theta parameter in your slides related to actual physical material parameters?
I'm not sure I remember where it was. Let me check. Was there a theta parameter?
Or is it related to the place where you said you will incorporate material information to your sketch system?
I'm not sure where that was.
Okay.
but we don't really have any physical parameters. Yeah.
Or
it's
actually,
not
do you think it would
yeah.
be worse to incorporate this in the future? For example, if I want to sketch, I don't know, different if the underlying surface like coming from different materials, would be
Yes.
useful to kind of incorporate this information into your sketch system.
For sure, it would be super interesting to kind of have a link to the physical art space, because so for now our surfaces are very simple. Actually, that's why I wasn't sure what you were referring to, because we just have kind of minimal surfaces. We don't work on their geometry a lot, but I agree it would be super interesting to kind of think of, okay, how a surface like made of different elasticity material will kind of stretch across this kind of armature that are the strokes. So yeah, that would be super interesting. Yeah.
Okay, thank you for the answer. And the next question is for Duygu. Like for your secondary motion paper, is there a specific reason that you only train on sphere? It is so great that to see just train on sphere can generalize to different shapes. But we're just curious whether you have considered to train on other primitives like a thin sheet or like or a bunny or other primitives.
Yeah, I mean, our initial choice of sphere was we thought it's a good primitive to approximate more humanoid type of characters like their bellies, etc. We did have some experiments where we also tried to add like some cylinders, but we did not do more thorough experiments. Like the results with just adding cylinders did not improve significantly, but I think it would be interesting to add like more thin sheets, maybe for the ear of the mouse, etc. It was a little bit more experimental and ad hoc choice.
Oh, I see. Perhaps a follow-up question is that do you think like, for example, like the curvature of the training data influence like, for example, the generalization? Or what are the key ingredients in order to influence, like to determine whether this is a good primitive to train?
Yeah, I mean, that's a good question. Actually, like at some point we are thinking maybe you may not even need a lot of primitives, but the current network basically looks at only this local neighborhood. So it might be even possible to come up with a list, like a list of small local patches, and you just train on them. So you may not even need a primitive. But yeah, I think as you add more data that will be similar geometrically to your testing results, you can expect that it's gonna generalize better.
Oh, sounds good. Okay, now next question is for Emilie. So this is, I think this is a very, very interesting one. So in which applications do you think this 3D mid-air virtual sketches will be useful? Because there are some, for example, there are some scenarios probably people prefer to even draw things on a 2D interface. Like, do you think which application people would really want to draw things in 3D?
Yeah, it's a really interesting question, and one like we come up with like we encounter a lot, because I mean, yeah, you can always say it's easier to draw in 2D. There are more tools. You can do it just with a physical tool. Well, I think 3D sketching really shines is that you can kind of like have a bit this direct expression of your 3D shape that you have in your mind, without like this projection step that when you do into the sketching. So like you can really externalize your idea in complete detail. But compared with sculpting or modeling, you still have this advantage of sketching that you define your idea or your shape with very few strokes and not like completely define it still. So I think that's where it's interesting. So kind of ideation of 3D concepts.
Okay, that's interesting. Okay, and the next question is for Duygu, and then is that we're just curious, like how many training examples are generally required for your detail enhancement paper? Because your network is mostly defined locally. We believe that network should be quite data efficient.
Yeah, I don't remember the exact number, but it was, as I showed, like three types of scenarios. Like we had two different types of skirts, and then we used like several motion sequences, mostly from Mixamo, and then we also had this like single sheet of cloth, and then trying to exert some forces to that. We never like did more analysis, like, okay, what is the limit? Can you make the training data more smaller and so on? But it was not a lot of different types of garments.
Yeah, that's good to know. It's hard to get such a large type of garment data set, so it's will be super great if this is like data efficient. Yeah. Right. Okay. And another question for Emilie is that how would be do you think, is there any benefits to, for example, record the direction of the stroke? Because right now people just draw a stroke. I believe this like you could treat it like an undirected graph edge, I guess. But is it useful to kind of record the directional information so that it could be used, for example, help determine which stroke should be connected to which one or something like that?
Yeah, it's a pretty interesting idea. We didn't try to explore it. I guess like, yeah, because you do tend, like, I guess your motions are maybe different at the start and at the end of your stroke, right? So maybe, for example, you could expect more imprecision near the end. I'm not sure, it's just a guess, but it could be interesting to study that kind of. For example, Rahul at DGP did some studies of imprecision in VR, and it would be interesting to see if there is a pattern that you can exploit in this kind of neatening beautification techniques. Yeah.
Okay, sounds. Looking forward to like in the future you incorporate this information. Yeah, and the next question is for Duygu, and then so you mentioned in the talk that those neural features or neural textures, that kind of thing is not that easy to interpret, and we're just curious about this property when we want to use the ML model to do a design tool, because if it's not easy to interpret, if we want to use that as a design tool, then would it cause any difficulties for artists to, for example, edit the result? For example, if the detail the network adds, the artist doesn't like that, is that how easy it is to control that edit detail?
I see. That's an interesting question, and I guess I may not have the perfect answer yet. I mean, in all these cases, basically the network just learns these features by looking at your training data, and all these networks are trained specifically for like one case. Like you have one network trained for one character, you have one network trained for like one particular target garment. It might be interesting to see, like, if you have one such network, like, can you at least do some maybe fine tuning with a very few examples, and then the network adapts? Then that could give the artist a way of control. Like you do maybe longer training with many examples, but then you also have this ability to just provide a few examples, and then the network can adapt. Then the control could be like giving those additional examples. We showed some examples of this by like trying to adapt the network to maybe like different background images, because that also determines kind of the lighting, etc. The network is able to adapt like with a few examples. I guess changing the whole appearance might be a bit more tricky, but I think it's definitely very interesting direction.
Well, sounds good. And it's like try to leverage the data dependency to make it into different styles or different designs. Yeah, right. That's cool. Yeah. Okay, and then the other one for Emilie is like, I think it's quite a big question. So far we have seen some modeling operations, for example, like your sketch system or Sylvia also has a swipe volume, and then you also mentioned that artists have some VR sculptors, and we're just wondering if we want to jump into this like exciting 3D modeling in VR or in just immersive environment in general, like what are some modeling operations that are still hard and still hard to achieve, and people really want those things?
So yeah, there are lots of tools that exist that correspond to kind of like the kind of map to a similar 2D tool. So yeah, there are things that are more like sculpting, like Adobe Medium also that Sylvia's project was kind of in the same vein. And there are things, there are also softwares to do kind of a primitive-based modeling, so with cubes, spheres, or with nerve surfaces. And there are also things more like poly modeling, where you pull on vertices and stuff. I guess what's really kind of missing, in my opinion, and that would be super cool, is kind of a way to switch the medium you use, like to be able to model some things by sculpting and maybe some other things by sketching somehow. I think that would be super cool. Otherwise, I mean, a lot of the 2D modeling metaphors have been brought to 3D, to VR, I think, in some commercial software or research projects. But yeah, nothing like kind of merges the approaches or tries to combine them. Yeah.
I see. So potentially we should have kind of like a unified representation of the shape, and every kinds of modeling operation could be kind of adapt to that representation, and then we can, like, I don't know, we can use your method to draw a rough sketch of the surface, and then for example use sculpting to add details if you want. Wow,
yeah,
that
would be
cool.
awesome.
Yeah, okay, understood. Okay, we have a last question for Duygu. Is that yes, so this your dynamic neural garment is super inspiring, and because you represent like a highly detailed garment with like a coarse garment, like without details and with a neural texture. We're just curious whether this could be like a general 3D shape representation. For example, if you want to represent a different human bodies, is it possible to have a smooth average human with texture on this human body so that we can decode that into all sorts of detail and then different humans?
I think definitely that's very interesting. So the real example I showed, actually the course template is the underlying human. I think humans are interesting. Something that I've been thinking about is actually hair. There is not much work in hair, but like, could you come up with some coarse meshes for hair and then learn these neural features to synthesize like realistic hair? That would be super cool.
Well, coarse hair sounds, I don't know, sounds amazing. I don't know. I just have a few hairs and then you can synthesize the entire. Oh, cool.
I mean, they use hair cards in traditional graphics. So maybe your primitives could be those type of coarse representations. But yeah, cool. I think very open research area.
Wow, for sure. That's exciting. Yeah. So okay. So I think that's the end of our Q&A. If you still have any questions, please feel free to leave comments or questions in the Discord. I believe our speakers will be happy to answer that offline. So now, thank you everyone for joining this colloquium, and let's also thank our speakers again. And we also want to thank our artist, Byron Eigensrisser, for making the fantastic poster for this week, and see you all next week.